So, let us continue our discussion on decarburization and how information about decarburization rate is useful in determining the endpoint. And I have been repeatedly stressing on the importance of endpoint control in oxygen steel making, because the process is very rapid. So, if you can control the endpoint very precisely, in that case the high quality of steel is assured and economic production is also assured simultaneously. Now, if you remember the impurity removal curve that I have shown in terms of a 20 minutes blowing plot. So, 15 and 20. So, this is time in minutes, and so I will only plot carbon. So, we start at 4.3 and it goes something like this, and then it ends a straight line sort of a scenario, something like this. So, this is, so initially you have a rate increasing, and then the rate becomes steady. So, this is the part where we have a straight line graph. So, dc over dt is negative, but it is constant, and then in the final period the tail end we have a dc over dt, or rate of decarburization, progressively decreasing with time. This, as I have indicated, this need not be 0 as I have labeled it. You must understand the steel will contain some carbon depending on the grade that we use to manufacture, okay, and that could be the your target chemistry. So, if this is wet percentage C in the metal, and accordingly if I translate this figure into a plot of decarburization rate, which is minus dc over dt. So, this is just like our notation, desulfurization, dephosphorylation I told you, DEP, DES, and this is decarburization, and the decarburization rate, you can say that if you plot for an equivalent period of time, then possibly it goes like this, and then the decarburization rate falls. That is a typical characteristics. Initially, it takes some time, for as oxygen is more and more supplied. So, the decarburization rate increases, more carbon gets removed, and there comes a steady state when we have the rate of oxygen supply matches exactly with the rate of carbon monoxide evolution, and that is the period of decarburization. And thereafter, there is not, you are supplying oxygen, but there is not much carbon. So, there is a mismatch, and the decarburization rate really falls as a function of time, and that is the same plot that we have. So, we are not interested in this part. In order to control the the most important significant portion is this particular portion, that how the decarburization curve tapers off to be able to simulate this particular region very precisely. So, this is, you can say that this is possibly not known to me. So, this is about 17 minutes. So, if I go from here and I get the corresponding carbon content. So, this is, so 17 to 20 or 22, whatever is the blowing time, that needs to be controlled. So, once we have the end of the steady state decarburization period known to us, which is the characteristics of a particular converter in a particular steel plant, and this part will depend mostly how you are changing the blowing pattern, whether you are blowing continue to blow the same oxygen or less amount of oxygen, and so on and so forth. So, this the end of the decarburization period typically in the bath will be more or less same if you go to a particular converter in a particular steel plant. So, and then typically that sometimes you may have to stop at 0.1%, sometimes you may have to stop at 0.1%, and this points needs to be. So, this your ability to predict this curve precisely in this particular region, you cannot afford to do innumerable for every hit you cannot afford to do experiments and then establish that for this grade of steel this is my curve, and then you can adapt that curve to the making of a particular heat. So, your ability to predict from this point onwards the characteristic nature of the curve is very, very important in order to control endpoint, because you will be making diverse grades of steel in the plant. You are not always going to make 0.01 carbon, you may make 0.1 carbon, you may make 0.12 carbon, you may make 0.17 carbon, and so on and so forth. So, therefore, it is very important for us to know the nature of this tailing graph, and I have told you that decarburization basically is a phenomena whereby melt phase transport of carbon is typically been shown to be rate limiting. So, it is not the chemical reaction, carbon oxygen reaction or carbon FeO reaction, dissolved carbon or slag FeO reactions. It is basically the transport of carbon within the melt phase. So, it is, if you are talking of this particular reaction, carbon plus FeO is equal to carbon monoxide and Fe, and then obviously you have you are talking about something like a slag metal reaction. You can, this is an artist's impression that I have a metal droplet surrounded by the slag, and possibly it is here that the reaction is taking place, okay? And therefore, the transport of, it is a two fluid mass transfer. It is not a, if you are talking about under steel making condition, it is not a solid liquid mass transfer, it is a liquid mass transfer, but still you have a boundary layer within the liquid side, and this is, since I have said categorically that it is a melt phase transport control. So, from the bulk of the metal, the carbon has to reach at this surface, and there possibly this reaction, if this is the slag part, not pure FeO though, okay, we must understand slag is a mixture of many other materials or many other oxides, and carbon is dissolved here, which of course does not have any unit activity. So, it is not pure carbon, we are talking about dissolved carbon. So, the carbon migrates, and then FeO and carbon bridges reacts at the interface, and so the chemical reaction is equilibrium. So, virtually we can say that there is an equilibrium concentration, which is, and the difference between the bulk concentration and the equilibrium concentration, this is basically the driving force for carbon to get transported to the reaction interface where carbon plus FeO. So, if a reaction takes place, so if you give you the temperature for example, and if you give you the partial pressure for a given activity of FeO or wet percentage of FeO, you should be able to calculate, and I have shown one such relationship, if I can write correctly, that wet percentage of carbon, percentage carbon into percentage FeO in slag, and that I think I wrote about maybe 1.25 or something like that. This comes out from equilibrium calculation. Okay? Under steel making condition, it is not, you cannot generalize it to all systems. Okay? And this is the oxygen steel making scenario, and then if you have something around 20% FeO, okay, and then you could say that this percentage carbon is going to be, if you divide it by 20, then you are going to get something like of the order of 0.05 or so. That is what is going to be the percentage carbon. Okay. What is this value? That is the percentage carbon, and that is equal to roughly about 500 ppm of carbon. That is the equilibrium. If the slag contains, and the system eventually approaches the equilibrium, which is it may reach equilibrium, it may not reach equilibrium. Okay. And so, if there is a slag metal equilibrium, eventually you will see 500 ppm oxygen dissolved in the metal, you will see 20% wet percentage of FeO in the slag, and correspondingly you will see about 500 ppm. So, that is your equilibrium carbon content, and it is this equilibrium carbon content minus this, sorry, the bulk concentration, which is higher than the equilibrium concentration, because carbon is going to be continuously consuming at the surface. So, C minus C equilibrium represents the driving force for carbon to diffuse. These sorts of a discussion are covered in any transport phenomena course. In metallurgy, you can refer to textbooks. I have a series of lecture notes which have been uploaded on YouTube on transport phenomena, where I discuss about this mass transfer, two fluid mass transfer scenarios, how to calculate the mass transfer coefficient, how to calculate the rate, so on and so forth. And I think these are about 25th, 26th, 24th, 25th and 26th lecture. In YouTube you will find under transport phenomena. I have my own channel there, and you can really read the more fundamentals about such kind of reactions, where chemical reaction is not the rate limiting, but the interfacial, the transport within the melt or the slag phase is assumed to be rate limiting step. So therefore, now since chemical reaction, so therefore we can say that the rate of decarburization basically is given in terms of a rate constant K, and the driving force for that is the representation. And as I said, that this part is going to be the important part. So it is, I would say, this is T is equal to 17, time is equal to 17 minutes, and this is concentration of carbon at C17 is, that is what I have found out, suppose is 0.4. This condition is known, and then I have to solve this equation, because this needs one condition, and that initial condition here represents corresponding to the time, because this curve can be now shifted to this, and this point can be merged along with the axis, and this could be interpreted. You can derive the integrated form of this equation either in terms of a factor t minus 17 or in terms of t minus 0 or simply t, depending on whether you decide to take this part and merge it with the this point with this. So you do a lateral coordinate transformation, and then it becomes a piece of cake. So you will integrate it, and then you will find out that the integrated form of the equation is C minus C equilibrium, and then you have C0, which is C17 in this particular case, and I said C equilibrium. This is 0.4, and this value is going to be exponential minus k into t. That is what it is. And I have written here kt, considering that this applies to t is equal to 0. I have done a coordinate transformation. So one could also do, I have applied the condition t is equal to 0. So C is equal to C17 is equal to 0.4. You could also do t is equal to 17, as I have indicated, and C17 is equal to 0.4, then a little bit of different form of this equation you will generate, but my equation and your equation then will be related, because by the coordinate transformation factor, as I have indicated, or the abscissa transformation factor that we have used in doing so. So therefore, it is understood that if you target a composition, how the composition evolves. What is this? This C is C as a function of T, how the melt compositions of carbon changes. So I would say Cc, this is concentration of carbon, and this I will say equilibrium concentration of carbon, this is C17 carbon, and that's because C for carbon and C for concentration are synonymous. So I will say Cc, and then I will say C equilibrium, C equilibrium C. So therefore, this is what it is. This is, as I have written it, C sub C, concentration of carbon, which is a function of time, and this allows you. So therefore, if you know the rate constant, how you will know the rate constant? The rate constant will be known. There is no shortcut. Rate constant is an empirical parameter, and that will have to be determined. And therefore, you have to, when you install an LD converter in your plant, in order to have this kinetic equation exactly established, you have to determine the rate constant, and then only you can have this kind of a model, then you will have a chance to predict the endpoint correctly. So unless and until the rate constant, which is a dimension of 1 by second, that is the dimension, and this needs to be specifically determined, and that to determine that you have to take samples. These are very difficult experiments on an industrial scale. You are talking about 1600 degrees centigrades, you are talking about taking innumerable samples right from the beginning. You may not take too many samples here, you may take only few samples, but identification of this point is very important, and from here you require a large number of points, so that you should be able to determine your rate constant, and rate constant is how you can find out the rate constant. The basis of finding out the rate constant is from this particular, if you plot Cc as a function of t on a logarithmic scale, the slope of the line will yield the rate constant that we know from our mass transfer fundamentals. I would like to note here that mention here that in the textbook that I have written and I have asked you to refer, there are some typographical errors as far as this portion of the discussion is concerned. So, I request you to take note of what I have written on the board and accordingly interpret, and in that light you interpret that whatever is there on the textbook as it is presented, and I hope that if the second edition comes out, I will get a chance to make corrections and amendments. Now, it is not desirable to interpret this line as a straight line. Okay? If you interpret it as a straight line, then of course, the piece it becomes very easy. In that case, you can say that dC over dt is going to be is equal to delta C over delta t, and this you can determine by considering any 2 points. But within this 3 minutes or 4 minutes of time, if the curve is actually it is a decaying curve, as you have seen from the expression, there is an exponential decay of the decarburization rate. This curve is far from being linear. So, it is not good to write that C minus C desired or C equilibrium and C0 minus C equilibrium. This perhaps is questionable, and I would say that a linear approximation is not good enough for you, because as we know, the exact rate equation needs to be employed, because we are talking about precise estimation of the rate constant, precise estimation of the endpoint, and that necessitates that the exact rate and as such you will see, because the high temperature measurements are concerned, K, the certainty with which K can be determined will vary from plant to plant. So, innumerable experiments, trials and adaptations needs to be done, and rate constants, for example, and these rate constants are going to be in mass transfer control process. For example, you will measure for during the first set of hits and the last set of hits, because the refractory design etc. Because of erosion and corrosion have changed. So, the vessel geometry etc. And maybe the wear and tear of the lance tip. Rate constant determined with a new lance and rate constant determined with an old lance may not be the same because of the wear and tear of the process. So, as such there is going to be some uncertainty in the measurements of K. So, precise estimation may not be always possible, and in view of that, if you make an approximation further, that decarburization C versus T is to be interpreted as a straight line. In that case, you will not be able to get any information, reasonable information about the endpoint. So, whatever I think in my textbook, you must remember that this K value, I have predicted temperature as a function. There is a table there, I do not remember the number of the table. That table shows how the concentration C varies as a function of time, but that can be done only when the rate constant is known. So, the table is constructed for an arbitrary rate constant of 1 per second, that is the value for which. So, implicit in that table, you may note, if you go back and have a chance to read through my text. So, this point got missing there, that the table has been derived by considering a rate constant value of 1 per second, and which is not there. So, these corrections are important. So, I do not want to go beyond this particular point, and I think I have made my point clear, that in order to have endpoint control, you have to first establish the decarburization curve as exactly as possible, and for that you have to take a large number of samples, and sample taking is not going to be easy, because the temperature is 1600 degree centigrade. You require a reliable probe, and once if you can take temperature, you can establish this graph. And now you can concentrate, once you identify this and graph is established. So, you know that from where the graph actually starts to deviate from linearity, and so from that point onwards, you can consider that the decarburization rate is deviated from linearity with a continuously decreasing rate. The curve is getting flattened and flattened, and this part needs precise simulation, and in order to do that, you require a good measurements of concentration versus time, and that will allow you to predict or calculate the rate constant, and then you have the process control model, that if you want to get 0.1 carbon, you use that rate constant value, and from this you find out that if this is 0.1, then what should be the corresponding time after this particular stage or this particular stage has reached. So, knowledge of kinetics is very, very important, and it is not necessary that overall at the end of the process the overall system is going to be how close the system is going to be equilibrium, close to equilibrium. There may be local equilibrium we are talking about, but there may not be a global equilibrium in the system. There may be more oxygen, there may be more FeO, and that we will see when we will compare different kinds of oxygen steel making process. Now, I will discuss, given this background, I will discuss now the bottom blowing oxygen steel making process very briefly. And as I have indicated that today LD steel making, and particularly the combination steel making of all the oxygen steel making processes, combination blowing steel making processes happens to be the most popular, because that gives us the highest maneuverability as well as highest profitability with a high quality of steel. So, we will discuss the bottom blowing oxygen steel making process, even though that process is not too popular, as I will show you why very briefly, but the kinetics of steel making is not going to change. You must, the thermodynamics and kinetics of steel making will exactly remain same. You are pumping in oxygen, only your mode of oxygen introduction is different. Okay? You are putting it from bottom. So, what does it do? That you are supplying oxygen, so the kinetics is getting affected. The mode of oxygen injection will affect the generation of convection currents in the system, because these combination blowing steel making reactors as well as the top blown oxygen steel making reactors, they all look same, they have the same shape. What is essential difference between them is the mode of gas injection, the how you inject the gas, and the quantum of gas is also dictated, and more or less the blowing practice is identical. So, it is virtually whether you are injecting from bottom or you are injecting from top and bottom, or you are injecting from top, that will determine that the starting intensity in the system, and that is going to determine the rate constant K. So, the rate constants for thermodynamics is absolutely identical, but the kinetics are different, and that is why the efficiency of reactions, this transport, these are going to be different in different systems. So, the kinetics are going to be different, and kinetics we know because our processes are mass transfer control, not chemical reaction control. Had the reactions been processes been chemical reaction control, I would not have said in that case the introduction of oxygen into the system would not matter. It would matter only whether we are injecting partially impure oxygen versus pure oxygen, and so on and so forth. So, thermodynamics of steel making, oxygen steel making need not be discussed. You have silicon, you have sulfur, you have phosphorus, you have manganese, and you put in oxygen, they are going to be all removed. So, there is not an iota of difference between the various versions of the oxygen steel making process. It is the rate, the blowing period may get reduced because the efficiency of stirring has changed now. Okay? So, the iron oxide content of the slag can reduce or increase because one system has started to operate much closer to the equilibrium because of if a system is more intensely stirred, I will expect that it will operate very close to the equilibrium. If a system is incompletely or not coherently stirred or not well stirred, I can expect that there is going to be inhomogeneities in the system, and therefore chances of hitting equilibrium is not going to be that much. So, bottom blowing oxygen steel making process, and this is similar. I have also shown you the 4 versions of the steel making when I started discussing oxygen steel making, and there I have shown you the same pear shaped vessel regardless of the type of oxygen steel making process. Okay? And in the case of top blown or LD steel making process, oxygen is put from the top plants at a supersonic speed. Okay? In the other cases, we really do not require. In this cases, oxygen is going to be blown at a much lower speed through the molten metal. Now, before I start the bottom blowing oxygen steel making process, I would like to make one point that gas injection, gas stirring is very popular in steel making because of the simple fact that gas stirring is very cheap, and you must understand that if you take 1 normal meter cube of gas, and that 1 normal meter cube of gas under steel making condition can be as much as 8 normal meter cube, assuming ideal behavior if you correct the pressure and temperature. So, the return of investment is too large, and of course, most of the gases we will see if you just want to do stirring. This case we want to do stirring, but at the same time we want to supply also oxygen because oxygen is a reactant. But in other cases we will see that we may just want to do stirring. In that case I do not want to inject a gas which will react with the melt, I do not wish to contaminate the melt, you know. So, subsequent to steel making all the stirring processes will use, for example, argon as the gas to stir molten metal because argon does not contaminate, even nitrogen will contaminate steel to a certain extent. So, there are several ways by which gases are injected into steel, and one such thing which we have seen is a lance, which is a vertical thing. We have also seen in the case of Bessemer steel making converter that air is introduced, and that is Tuyer, P-U-Y-E-R-E, and there is a third device also which we call as porous plug, okay, which looks something like, it is a ceramic artifact. It could have channels, you know, it is a prefabricated structure, and there could be number of pores through which, and there is a pipe here through which the gas is going to be introduced, and the gas is going to be released from all those pores, because there is a directional porous plugs are also there. So, there is going to be channels, innumerable channels. If you look at this, the cross, it looks like, you know, the frustum of a, you know, cone, actually a portion of a cone. So, this is typically, if you draw it like this part does not exist, then this is actually a solid cone, that is what it is. So, all through the solid cone, and then it is truncated, the top is removed. So, you see there could be slits, vertical slits through which gas is going to travel, or there could be interconnected pores, micropores through which the gas can be. So, this sort of gas injection passages are introduced during the time period of during the period that they are fabricated. These are straight tubes, vertical tubes, tuyers, and this is porous. All these are consumable under oxygen steel making condition, all these are consumable to a certain extent. Okay? They do not last perpetually because of the intense heat which is being generated. So, just like the vessels need relining from time to time, these gas injection devices are also. So, this is with reference to top blowing LD converter, this is with respect to the Bessemer converter. We will see that this device, a Tuyer, is being used in bottom blowing oxygen steel making process also. And porous plug we will see in the combined blowing steel making process, at least in one version, which is the bath agitation process, there where the requirement of gas. So, when you have to have very large gas you want to put in, this is not a good one because there are only pores and slits. So, the resistance to flow is really very large here. So, when small volume of gas is to be introduced, porous plug suffices, but when large volume of gas is introduced, you know, you have to have either a lance or a Tuyer. And gas injection, as I would say, is important because gas injection, the cost is cheaper most of the time we find. It is easy to maintain, and you can imagine putting in a refractory propeller inside steel bath and stirring it, and then the refractory itself will get eroded and contaminate steel, and particularly if you are talking of beyond primary steel making, beyond LD steel making or the final stages of steel making, then the wear and tear of the impeller could jeopardize the quality of steel. And this is also, this produces very intense stirring. Impeller, if you rotate, I think at the same specific energy input rate, it is now proved, or one can show that an impeller stirring is going to be more intense than the gas stirring, but the gas stirring has its own advantages, particularly towards the later part, because the simple fact that gases, particularly when you use inert gas. We will see this in secondary steel making or ladle metallurgy steel making, particularly when you blow inert gases and you take extra precaution not to contaminate molten metal, even though an impeller starting could be economically more advantageous. It has, of course, the material consumption, these are, you require only a porous plug. The porous plugs are far more cheaper than these impellers. For example, there is a process of KR process of desulfurization. KR process of desulfurization, this is a pre-treatment process, okay, where one would use intense amount of stirring, because you have, molten metal temperature is going down, hot metal temperature. So, you want to impart stirring as early as possible. So, you require a far more efficient stirring, and therefore, the KR process, and this is the impeller which is used in the KR process to start the contents for desulfurization, where you want to mix the powder, liquid and so on, and all desulfurization agents. But that is besides the point. But as I said, that when you have large volume of gas is to be introduced, we will use lance and tuer. Small volume of gas we will use porous plugs. These are artifacts which will remove, which will require periodic replacement or refurbishing, and therefore they are to be treated as consumable item in the whole process. More elaborate discussion of gas injection, different types of gas injection. So, right now what we are talking about is a reactive gas injection modeling or reactive gas injection scenario, because the oxygen which is introduced into the system, it not only starts the system, it also reacts with the hot metal as well as the metalloids which are dissolved in. Now, in the Bessemer process, we have seen and I have made categoric statement that during the period 1932 to 1935, people actually tried to put in through this kind of an tuer oxygen gas into steel making converter, okay. But because pure oxygen would produce, if this represents the base of the vessel, and in this particular vicinity the amount of heat liberated because of metalloid reaction on oxygen, if you that this tuer gets almost consumed in no time itself, the tuer undergoes melting, and that I have mentioned also. So, this shows you one tuer through which oxygen is injected now, and if you inject oxygen in that case you have problem with the local refractory erosion. The refractory will undergo erosion, making it, exposing it to high heat, and as a result of which what happens, the tuer undergoes degradation very quickly. So, obviously, when you are talking of bottom blowing oxygen steel making process, the same design of the tuer that was used by Bessemer will not work here, and the whole tricks of making bottom blowing oxygen steel making process is the use of what is known as a coaxial. So, it is the same kind of a vessel that one would use. So, that pear shaped vessel which is our trademark steel making vessel. Okay. So, that is the vessel geometry, and now when you have a bottom blowing steel making process, you have tuers here, but these tuers, as I say again, are not the same tuer as those used by Henry Bessemer long time back, and indeed there are, these are called coaxial tuers. The tuers are actually coaxial. So, if you take one tuer and it looks like this. So, there is a this and there is this. So, that is that is what it is. So, it is through this passage that oxygen is going to be passed. And if you look at the cross section of this, you see a circle here, the inner circle which I should draw by white chalk, and then you have an outer circle. Okay. This is the cross sectional area. top view of the coaxial tuyeres. These are two concentric cylindrical pipes. So, there are two gases which are flowing here. Inside one is oxygen and the outside one is a hydrocarbon gas, like propane, etc. Okay. Now, when you use hydrocarbon gas and oxygen here, so because there is an intense heat, the cracking reaction takes place. The hydrocarbon will dissociate, and as a result of which, what happens is you have cracking reactions are known to be highly endothermic reactions. So, there is a local consumption of heat, and that what it does, let me now erase this and then explain that what it does. Because of the cooling, what happens is on the refractory, so this is, so this is my refractory and this is the coaxial tuyere and this part is my metal. That is what it is. So, one tuyere I am showing here, that how does it goes. So, this is the metal phase, and then what happens is that because there is a cooling action here, and in that case what happens is basically you have some sort of a accretion switch develop, So, these are molten metals which are solidified here, and solidification you require additional surface area, as you all know. So, the refractory is a good nucleating side. Okay. So, where because of low temperature, because of the cracking reactions, what happens is that, but this is because you are blowing hydrocarbon. So, as a result there are pores also, there are channels which are, you have high pressure. So, through which the gas will go out, hydrocarbon gas will go out, and this basically gives rise to some kind of a protection. So, these are passages or cracks in the deposited metal. So, you say we call it as a mushroom kind of a shape, mushroom shaped structure that grows around the OBM the bottom blowing oxygen steel making process. This is also called in America, it is known as I have indicated that the steel making process, they have a if you go to Europe, most of the people will say BOF, but if you go to America, people will talk about BOS, basic oxygen steel making process. So, they are one the same thing, and the bottom blowing process in Europe is known as OBM, oxygen bottom blowing MAXFET. On the other hand, in US or North America, it is known as QBOP, basic oxygen process, and Q stands for quiet, because the injection of oxygen from the bottom really does not produce too much of a noise, external noise, and hence this. So, this is the European name, this is the American name anyway. So, this is the mushroom which develops and which now when you blow oxygen through the mold, so the oxygen goes out, cooling, the tuyere gets protected. So, one problem is solved, okay? But that does not mean that you can perpetually use the tuyere, and still you will have, because the refractory iron oxide refractory interaction, etc., refractory will get damaged, but certainly the scenario is far more better than with a single tuyere, or a tuyere which is carrying only one single gas like oxygen in this particular process. So, this has really solved, this is also known as the Savard-Lee tuyere, after two scientists, okay, who that hydrocarbon could be blown. It was a great solution to an existing industrial problem, and this not only protected the refractory, but also protected the tuyere to a large extent, and making the oxygen steel making process really commercially viable. Okay. Now, according to this, so when you have molten metal here, now you do not have an emulsion. When you have a top jet, Then you have created an emulsion, and then you have the bottom part also. There are two distinct regions in an LD converter, and I have told you that the reaction in the bulk metal phase in the LD process is not so large, because of the simple fact that it is not quite well starred. The energy transfer from the top jet to the bulk steel is not quite significant. So, the bulk is poorly starred in LD steel making process. On the other hand, when you inject bottom blowing in the bottom blowing steel making process, when you do not have oxygen, so what happened? You do not have an emulsion phase here. There is no way you can generate emulsion. Emulsion is generated because of the impingement of the supersonic jet on the metal surface, and that helps ejecting the droplets. Here also droplets are going to be ejected, but minimal number of droplets that cannot, and these droplets are going to be large droplets, because you do not have that kind of a large shearing force between metal and gas which is available, or metal and slag which is available in the LD steel making process. But that you inject oxygen from the bottom, you have all sorts of tuer arrangements here, okay? 12 tuers, 6 tuers. So, if I would have drawn the bottom view, then you could have seen all those tuers, that how many tuers are there, whether they are symmetrically distributed, all sorts of patterns are going to be there. And what they are going to make? They are going to affect the starting of the bulk phase, and as a result of which what happens, the efficiency of steel making process or the refining reactions can be drastically affected. So, the tuer design, the number of tuers, the number of and their layout on the base is going to affect the fluid flow pattern in the system, and this fluid flow is going to affect my K factor, which I have said that it is rate constant. For mass transfer problems, it is a function of the velocity, and as a result of which the design of the tuer, their number, the gas flow rate of course is an important variable, all those will affect the kinetics of the reaction itself. So, because you inject oxygen from the bottom, the gas liquid coupling is far more efficient here, okay? Directly the momentum is exchanged between the gas and the liquid. So, you may have the gas may be rising because of the gas is rising because of its buoyancy, and as a result of which, as the gas flows up, because there is a huge density difference between the gas and the liquid, and as the gas flows up, you have a good amount of stirring, and if you have since you will invariably have slag metal interface, slag floating on the top, so there is going to be good amount of slag metal mixing in the system. The flow rate as such is very, very large, 50 normal meter cube per ton per minute, something like that. So, it's 5 normal meter cube per minute per ton, not 50, okay. And then the oxygen flow rate. So, we have number of tuers, so good intense gas flow rate, and that the gases have a large amount of potential energy because of this metal depth, and which is caused by the large scale density difference. So, very intense amount of stirring, the slag metal mixing, while the slag metal interfacial area is much larger in the LD steel making process, but the mixing which will eventually determine whether the system is operating how close to the equilibrium, that the agitation and the slag metal mixing is far more efficient in the bulk of the liquid. So, you have only one single phase, no emulsion, but the bulk is very well stirred because of the correct design of the bottom tuers, and as a result of which what happens, the blowing time gets reduced here. As a result of which what happened, if you compare these two processes, you will see that you have significantly larger FeO content in the slag, because the system is quite away from the equilibrium itself. There is no top blowing gas here, there is no bottom blowing gas here, but if you compare on a one-to-one basis, and virtually here the stirring is extremely weak in comparison to the stirring that is generated here. So, this system is extremely well stirred, and as a result of which the slag metal mixing is very good, and as a result of which the chances of slag metal in equilibria, the possibility of slag metal equilibria is far more, and I would say make that categorical statement that slag and metal are operating very close to the equilibrium here than it is here at the temperature and pressure under consideration. Now, in this particular case, what we have seen in LD, there is a phenomena called sloping, and this is very because the system is not well starred, and I have told you that you have droplets which are being ejected. These droplets, as the carbon monoxide, droplets of metals, as the carbon monoxide bubble escapes, the droplets become heavier, and then the droplets come back, and these droplets are pure. And what happens is that the bath is not well starred. There are regions sometimes somewhere where what happens is the hot metal accumulates, and it has lot of carbon into it. Okay? And so, if the inhomogeneity, because it is not starred, it is an inhomogeneous bath. Okay? Inhomogeneity is high. So, if carbon gets inhomogeneously distributed, and there is a pocket here where we have hot metal with rich carbon content is available, and if this kind of a it is exposed, it gets exposed to molten metal, because it is because it is lighter, it is floating up, so there is a good chance of interacting with oxygen. And what happens is, at one point of time, there is a vigorous amount of explosion which may take place, generating carbon monoxide bubble, because you have a large amount of carbon. All this carbon present in this pocket of hot metal has all of a sudden been exposed to atmospheric oxygen, and as a result of which what happens is you have a huge volume of carbon monoxide which is generated. Okay? The scenario is equivalent to if you take a Coke bottle, shake it, and then open the cap, and then what happens? The cola comes out, and it is exactly the same way that you have the material. What it comes out? There is a gas, metal, slag, everything comes out. Now, as a result of which what happens is your yield becomes decreased. You have lost some amount of hot metal, okay, iron from the system. So, therefore, we would compare that because this system is more efficient, we will say that the chances of such phenomena taking place is extremely rare. And I think in this particular case, I would say sloping is rarely, perhaps never. Okay? On the other hand, sloping, if you do not play your cards well, could be quite sporadic, particularly in LD steel making process. Now, despite we know that it is quite good system, it operates close to equilibrium. For example, here under the same condition, the FeO content of the slag could be about 20%. On the other hand, the FeO content of the slag could be about just 10%. End oxygen content could be about 600 ppm. End oxygen content could be about 300 ppm. So, this oxygen here, dissolved oxygen, is equilibrium with the FeO of the slag, and you can calculate the corresponding carbon content. So, the system, these are the figures which tells us that. So, more yield is certainly there. So, one advantage is more yield is there. More yield means more profitability, more money, okay? That is there. And we also have, as I have indicated, very rarely incident of sloping in this particular case. Iron oxide loss is rare, and we have less amount of oxygen, which is also important, because we will see that in the subsequent stage which we will discuss, that following primary steel making we have to have what is known as deoxidation, removal of that dissolved oxygen. So, the deoxidizer requirements are also going to be small. But despite these advantages, which are very well documented, which you know from our understanding of the underlying theory, the OBM process has not been very popular, okay? Because of the simple fact that the maintenance of the bottom refractory is still a problem, the maintenance of the wear is still a problem, because although one could solve the problem, but nevertheless these require the vessel turn down time, I mean relining time becomes quite frequent in comparison to a top blown where no such refractory replacement. So, the bottom needs to be periodically replaced or frequently, much frequently replaced, or the vessel bottom blowing steel making process requires more intense maintenance of the converter lining on the bottom than the top blown converter. And most importantly, that you tend to generate more amount of hydrogen in steel, and hydrogen is extremely dangerous. Where from hydrogen comes? Because you are putting in hydrocarbon as a gas, the cracking takes place, and hydrogen has good solubility in steel at 1600 degrees centigrade with 1 atmosphere partial pressure or pure hydrogen. The solubility of hydrogen is 28 ppm. Of course, it is not pure hydrogen ppm, but you can expect 2, 4, 5 ppm hydrogen. It is not, in this particular case, it is not so unlikely. So, and the tolerable, most of the good quality steel require hydrogen to the extent of 1 ppm. For example, railways, you may have read in every winter that railway line cracked, and there are some accidents, okay, because of the cracks in railway line, and hydrogen is known to be a culprit as far as causing failure of the railway lines, and therefore, the Indian government or the Indian Railway insist that unless and until you have vacuum degassing, which brings hydrogen to 1 ppm or less than 1 ppm, they will not buy steel and turn it into railway lines, etc. So, this sort of a requirement, low hydrogen content, cannot be satisfied in oxygen steel making process. So, therefore, what happens is that top blowing steel making process not so good, bottom blowing steel making process, it has its own advantage. But we can see now, if the two processes are given to me, I can see that, look, I have a process here close to equilibrium, better yield. I have a process here, where there is a, reaction rates are quite fast, etc. Can I not, create a win-win situation by combining the best parts? I devise a reactor where I have features of top blown and features of bottom blown, and yet the system will not suffer, the disadvantages. So, we will extract the characteristics of the bottom blowing steel making process as well as the top blowing process, and perhaps a win-win situation is what is known as the combination blowing steel making process or the bath agitation process. And particularly the bath agitation process, we will see solves many of the problem of the two reactors that I have discussed today, whereby we will not introduce oxygen, but we will introduce argon. How much argon? Only 2 to 3% of the top volume of the gas, barely small amount of argon we will use, and thereby not through 2 years, but through porous plugs, because it is a small gas injection. I have made that statement that if we want to inject small gas flow rate, the best thing is to do is the porous plug. So, argon can be injected from the bottom, oxygen can be injected from the top, and that is the configuration of the bath agitation process. And if you use argon from oxygen from the top and oxygen from the bottom, and that becomes a combined top and bottom blowing oxygen steel making process. But the moment you start injecting oxygen from the bottom, okay, you have to go for coaxial tuyeres, and as a result of which higher hydrogen content of steel, as well as more frequent maintenance of the bottom. So, bath agitation process, whereby you use a top jet transferring oxygen or supplying oxygen and argon from the bottom, that perhaps seems to work well, and the worldwide trend now is to go for more and more bath agitation processes, okay, as far as oxygen steel making process is concerned. So, today if a new plant comes up, obviously it is going to be have two options, electric arc furnace or oxygen steel making process. In oxygen steel making process, we will not do this, but we will go to a combined blowing process, and that I am going to discuss in tomorrow's lecture.